Apple II wire-by-wire build, EPROM Raster Generator. I'm Dr. Matt Regan. Over the last set of videos, I've made a raster generator on a breadboard. This included a horizontal counter, a vertical counter, a memory interface with shift register, and finally, the analog circuitry required to generate a composite signal. With this, I was able to generate an image on a TV screen. Now this image is stored in EPROM, but I really want to be able to access images stored in RAM. Then we can actually play the game. More specifically, I want the 6502 CPU and the raster generator to share some memory. One way to do this would be to use dual-ported RAM, but I really don't want to go down that pathway. To figure out how we might be able to share memory, let's look at the 6502 timing diagram in a bit more detail. Remember that phi2 is clock, so address is only valid while clock's high. We also see that the read appears to occur on the negative edge of clock, and the write date is mainly valid while clock's high as well. What this tells us is that the memory access for the CPU seems to only occur while the clock's high. This means while clock's low, we can use it for video memory access. This sort of sharing of the memory is called time division multiplexing. And what we need is a circuit that can take both the video address and the CPU address and only allow one to have access to the main memory address bus. A circuit that does this is called a multiplexer, and we use the select signal to choose whether it's the video address or the 6502 address that goes through to the system memory. When select is low, we want the video address to go through, and we want the 6502 address to be blocked. And similarly, when select is high, we want the 6502 address to be able to go through to the system memory, and we want the video address to be blocked. In the Apple II main block diagram, we can see the address multiplexer here, and it chooses between allowing the 6502 to have access to the memory or the raster generator to have access to the video memory. A chip that we could use to do this multiplexing is the 74HC257. It has 4 sets of 2-to-1 multiplexers. When pin 1 select is low, the upper pathway is selected. But when pin 1 the select signal is high, the lower pathway is selected. As before, we can put a shift register on the data bus, and this is how we convert a byte of data into a pixel stream. There's quite a lot of complexity in the clock circuit, and we have 2 different clocks shown here. I'm planning to do an entire video on how the clocks are generated. In addition to the counters and all the logic associated with them, we need to add a lot of components to make this display system work. We need a 4-bit adder for address correction, and we actually need 4 of these multiplexer chips to select between 2 16-bit buses. This means the entire design has about 20 chips, and even then the system is very fixed, with no programmability at all. We could look to use a chip like the TMS 9918, however it only has a 256 by 192 pixel resolution, and we need 280 by 192. So I'm going to use an EPROM as the raster generator. Admittedly, this wasn't a very practical solution in the 70s, but it makes a lot of sense now. Before I do though, let's quickly go over computer memory again. Remember that I said a set of pigeonholes full of different coloured rubber ducks is a good metaphor for computer memory? The main thing is that each pigeonhole has to have a unique number, and in computer science, we generally start at 0. And this set of pigeonholes with coloured ducts is actually a metaphor for what's going on inside the chip. Using an EPROM is actually pretty straightforward. We have a set of pins called address pins, and they tell us the pigeonhole number. Here they're represented in blue, and the numbers presented in binary. And then we have a set of data pins or output pins. These are orange, and the data at the location pointed to by the address is output in binary. And remember that each duct colour has a corresponding binary number associated with it. Conceptually, the pigeonhole number comes in at the top, and the associated duct colour comes out the bottom. I know I've gone over this a number of times now, but I want people who haven't watched the previous videos to be able to understand this video. Anyway, revision is good. The other thing I want to go over again is the octal Dtype flip-flop. It has 8 wires coming in and 8 wires going out. This is a bit like a single pigeonhole, and it can store one 8-bit value internally. These flip-flops have a clock signal, and the data internally only ever gets updated on the positive edge of the clock. Data presented at any other time is just ignored. Watch the clock signal again. What I want to do now is put one of these Dtype flip-flops on the output of the memory. When an address is presented to the memory, the associated data is presented on the output pins. But it doesn't actually get latched into the flip-flop until the rising edge of clock. And if output enables low, it'll be presented on the output of the flip-flop at the same time as well. Given that all this information is just data, we can actually represent the duck color as another address. And now I'm going to do something very tricky. I'm going to connect the output of the flip-flops back up to the address lines of the memory. This thick blue wire represents a bus, and it's really just a set of 8 wires running in parallel. Let's start with the assumption that the flip-flops contain 0. This is output onto the bus. It flows around back into the address lines of the memory. The memory does the lookup. It sees the red duck and transmits that to its output lines. Then on the next rising edge of clock, this gets latched into the flip-flop. So we've gone from 0 to 2. Now the 2 is presented on the output lines. This goes back to the memory. The pink ducks read from location 2. This goes to the output lines of the memory, which are also the input lines to the flip-flop. On the next rising edge of clock, this gets stored internally within the flip-flops and then presented on the output pins. Now this cycle continues, with a new output being available on the rising edge of clock. Hopefully you can see that this circuit will just cycle through the addresses 0, 2, 6, 3, 8, and back to 0. Once it reaches 0, it just goes through the same cycle again. Now I want you to think for a moment how we might be able to use a circuit like this as a raster generator. It certainly is much simpler, and it'd be nice to avoid all the counters with the AND gates and OR gates. Remember that the high-res image starts at location 2000 in hex. Let's say we have some sort of mechanism that puts us at location 2000. Then the memory at location 2000 hex contains the number 2001 hex. This causes us to cycle to the next address, which is 2001, which contains the location 2002. The data at 2001 becomes the next address, which points to 2002, and we read the 2003. And we just keep doing this until we reach the end of the active period of the scan line. So we step through a total of 40 locations. Now at 2027, I need to step off into some other location in memory, which controls the blank area and the sync signal, and then I want to step back to the next line, which is 2400 hex. Then at 2400, I go to 2401, 2402, and so forth, continuing until I hit 2427. So in this way, the number stored is acting both as the horizontal counter and the vertical counter. But I'm not actually counting anything. I'm just remembering the next location to go to. There's quite a bit of complexity in programming this EPROM, so I'm going to devote a whole video to it, which will be coming up next. We need to figure out how to add this EPROM Raster Generator into our existing Apple II design. So far, we have an address bus and a data bus, which connects the CPU to the SRAM and the EPROM. It's actually quite straightforward. We just feed the address bus into the EPROM, the output of the EPROM goes into a set of flip-flops, and the output of those flip-flops goes back onto the address bus. We also need a shift register like we've seen in the previous video to convert 1 byte of data into a bit stream. Now we have 2 devices though that could drive the address bus. This is our character clock. When clock's high, we want the 65C02 to drive the address bus, and when clock's low, we want the raster generator to drive the address bus. The bus enable pin on the 65C02 is active high. So if we connect BE to clock, it means the 65C02 will only try and drive the address lines while clock's high. Conversely, the output enable signal on the 74HC374s is active low, so if we connect these to clock, the raster generator will only write to the address bus while clock's low. So the wiring's pretty straightforward. Hopefully you can see, by using BE on the CPU and the output enable on the flip-flops, I've actually avoided the need for a set of multiplexer chips. Finally, to make sure that we're only performing a read while clock's low, we just need a pull-up resistor on the read-write bar line coming out of the CPU, which we've already done in part 6. You may be wondering why I switched to the EPROM Raster Generator rather than using the circuit that I've previously developed. Well, I want this machine to be a testbed for the Turing 6502. So hopefully you can see some similarities between the EPROM Raster Generator and the rulebook in the Turing 6502. Eventually I want to condense these down to one single circuit. After multiple requests, I'm going to make a schematic diagram, and I'll make this available through GitHub with links below. I'm using the free KiCad software, and once you get used to all the shortcuts, it's actually very powerful. Now this is one of the features in KiCad that I particularly like. When you draw a line, you can just press Insert, and the line gets replicated just where you want it. The same thing happens with labels. You just label the top element, and if it starts with a 0, it'll auto-increment every time you press Insert. This copy and paste also makes it easy to design a circuit. I made a template with a static RAM, and then I'm copying the address lines onto the EPROM and the CPU itself. Sometimes it does take a little bit of relabeling though. Now we'll copy and paste the ground rail. Same with power. I need to connect the address bus up to the Arduino. The order here is reversed from A7 down to A0. I need to relabel the wires, and there's probably a much easier way of doing this. If you know, leave comments below. I'm not going to include the circuit for detecting C1000 yet, because those slots are still empty on the prototype board. I'll come back and do that a bit later. Now I'm going to connect the data bus to the Arduino, and remember I made the wiring mistake, so I'll actually replicate that wiring mistake here. I don't need to connect all the address lines between the devices together, just labeling them's enough. But having buses throughout the diagram just makes it more understandable. And to connect a wire to a bus, we need to use these 45-degree bus connectors. Next, we can lay down the bus, which are these thick blue lines. We then label the bus with the square bracket nomenclature. Here, it's A square bracket 0.18 close square bracket. The reason I'm doing the entire schematic diagram at this stage is so that it makes it clearer how the video circuit's added onto it. Now I want to lay down the data bus, and I find it really confusing when buses cross over each other. But if a bus goes over a wire, and the wire is not connected to the bus, it's pretty clear that the bus is just going over the wire. All the inputs to the CPU need pull-up resistors. Here there really isn't space for the pull-up resistors, so I think I'm just going to move this address bus out of the way. And it solves the bus over wire problem. Now I'll put the resistors in place. And I'll just route the address bus over the top when I'm done. That's pretty much where we got up to in the build in part 7. But now I want to add the EPROM with the flip-flops on the output. This structure actually has a name. It's called a finite state automata. Place the EPROM and the two octal Dtype flip-flops. I need to supply ground and VCC to both of these chips. The first thing I'm going to connect is the data output from the EPROM up to the input to the flip-flops. And I can use this copy and paste function in KiCad to make that really quick. I'm going to make this bus the V-bus, which stands for video address. You may have noticed that the order that I've labelled this V-bus is different to the labelling on the chip, and I can do this because it's an EPROM. I just need to make sure I make a correction when I program it. Now that that's done, I'm going to implement this on the breadboard build. The output from these flip-flops go directly back to the address bus, and using the output enable pin, I can make sure that the output's only written while clock's low. This gives the raster generator access to the memory without conflicting with the CPU. Slight correction required there. Power and ground to the EPROM, and I'll ground the EPROM enable pin. Now we just connect the address bus up to the address pins of the EPROM. This really is a very simple raster generator circuit. For now I'm just going to ground the upper address pins of the EPROM, but eventually I plan to use these for the various text and high-res modes. Eventually these will be controlled by the Arduino, and they'll be set and reset based on the soft switches at C1000. That's it for the build. Next video will be on programming the EPROM. And don't forget, like, subscribe, and share.